Okay, so this is our first part of presentation, and I am the student usually. My present part is about introduction and Homer Pro part, and my partner Samira will do the Simulink and controller system part. So for my part is to presentation about designing and simulating a hybrid power system for Makkovik laboratory. So I separated it into three parts: the introduction part, the methodology, and the results in Homer Pro. For part one, the reason why we choose Makkovik is because it is an Inuit community in Canada, which is isolated from the mainland. It means that it heavily relies on diesel power generations and lack access to centralized grid infrastructure. You can see the map of the Makkovik is nearby the sea, and it contains almost 230 people. Because of lack of the centralized grid infrastructure, the Makkovik struggle to acquire reliable and reasonably priced electricity. Like traditional fossil fuel-based generators lead to high energy cost, undermine energy security, and worsen environmental degradation. In response to these challenges, we try to design a hybrid energy system. So this is the data we're collecting from the open data or from the Homer Pro. So you can see modeling the load profile is essential for determining renewable energy sources, optimal sizing and selection. Since public data on Makkovik's power usage was available, a load profile was created by adjusting the data from a similar community, considering the number of homes in each area. So as a reasonable estimate, the average daily energy consumption is nearly 10,655 kilowatt hour, with a peak demand of 1,548.97 kilowatt. Also, the average wind speed for each month in Makkovik has been shown in the top right figure. The data are from the NASA surface meteorology. It shows that wind speed is quite lower in the summer than in other seasons. The annual average wind speed is recorded as 8.53 meters per second at 50 meters height. Also, according to the GHI data, a large amount of solar energy can be used from April to August. So this is our methodology. You can see the design schematic for Makkovik. For each parameters, we choose different types of like wind turbine, PV, diesel generator, and batteries. For the wind turbine, we choose this 330 kilowatt, a huge wind turbine with the lifetime is 20 years, the height is 80 meters. Also, we choose this type of PV. We choose this type of PV design for the long-term reliability, with the replacement cost estimated at 3,000. According for potential future market fluctuations and technological advancement, we choose this high-efficiency PV, which is steady enough to withstand the relatively harsh local climate conditions. Their durable design ensures reliance against harsh weather, contributing to the system's overall reliability and long-term sustainability. And we choose this CAT 500 kilowatt diesel generators. We set the current fuel price is almost 1.8 per liter, and the capital cost will be 55,000. Also, we choose this SBS 3900 batteries. The nominal capacity will be 51.6 kilowatt hours. So for all these parameters, we create the models or the hybrid energy systems for the Makkovik to satisfy the peak demand and annually demand. And here is our result in the Homer Pro. It shows that optimization result. You can see it on the table. Also the power systems yearly data. It shows that the wind turbines contributes the largest share, generating nearly 97% of the total power. Also in these sections, you can see the analyzing various components and key performance metrics such as optional cost, net present cost, levelized cost of energy, and initial investment. Also, you can see the power system yearly data indicates that there is an 88,473 kilowatt hours excess energy generated and a 1,414 kilowatt hours emitted electric load, probably because of the demand not satisfied, and also a 3,858 kilowatt capacity shortage. So you all can also see, like as I said, the wind turbine generating the most part of the power, but also the PV powers produce around 33,000 kilowatt hours per year, and the diesel generators supplies like 11,208 kilowatt annually. So that is our hybrid system is fully satisfied Makkovik's demand. So my partner Samira will do the next part about the Simulink and the controller system part. Thank you for listening.
So in this section I'm going to explain the simulation model for the hybrid power system and provide control strategies such as MPPT. This slide illustrates model used to simulate the hybrid renewable energy system. The detailed explanation of each component is provided in following slides. Okay, this model can be connected in series and parallel to form strings or arrays. PV arrays consist of 12 PV modules connected in series, 35 PV modules connected in parallel, and each module is rated at 400 watts. This figure illustrates PV output current and power under different irradiances. The PV has 4 parts: DC boost converter, battery pack, and 3 phase inverter and PV cell. A wind energy system consists of 3 parts. The first stage is aerodynamic phase, the second one is mechanical phase, and the third one is electrical phase. This picture displays the power speed characteristics of wind turbine in per unit values, offering a clear understanding of how its performance changes under various conditions. According to this picture, the diesel generator includes diesel engine, excitation system, and synchronous generator. It operates effectively between 208 volts to a 600 voltage. The capacity of diesel generator is 500 kilowatts. Diesel generator as a backup system, it was first connected to a breaker before being directly linked to the load. In this slide, I plan to explain control strategy. The MPPT controller regulates voltage and current to maintain optimal PV performance. The battery power adjusts in response to excess or insufficient generated power. Besides that, when the load demand is lower than combined output of wind turbine, PV system, or diesel generator, the battery charges cause an increase in its output power and current. Various weather conditions are considered to access performance of dynamic models and control strategy. A PV system output voltage and current shown in this slide. Based on this figure, the MPPT controller manages voltage and current fluctuation to ensure optimal PV output. In this slide, you can see the wind turbine's power output across varying wind speeds. At the rated wind speed, the turbine reaches its peak performance. In addition, the output, voltage, current, and power of load shows in this slide. The peak load demand in Makkovik is 1,548 kilowatts, and the average load demand is 450 kilowatts. In this study, the breaker is used to represent both average and peak load. In conclusion, this study analyzes the feasibility and off-grid hybrid renewable energy system for a remote community. The purpose is reducing dependence of conventional energy sources and enhancing energy security. The research used Homer Pro and MATLAB simulating to evaluate various system configurations. The optimal setup includes PV panels, wind turbine, diesel generator, and batteries. Wind turbine plays a crucial role in our system. This hybrid system minimizes diesel use, low cost, and cut greenhouse gas emissions. This study confirms the system's reliability and environmental sustainability as a long-term energy solution for the community. Thank you.